Great to have Santhoshini speaking today. Santhoshini is a research faculty at TTIC. She graduated in 2023, got a PhD from Harvard, working with Madhusudan. Santhoshini has done a lot of interesting work on modern algorithmic settings, and so in particular sort of handling big data, limited memory handling, and sort of understanding what can be done using streaming algorithms or what cannot be done using streaming algorithms or other models which work with limited memory and large data. And she'll tell us all about it.
Thanks a lot, Madhur. So I'll get started. I'm interested in theoretical computer science, and more broadly, I'm interested in the design and analysis of algorithms. And my broad research goal is to devise canonical solutions to fundamental problems that are broadly applicable. And also to develop unified techniques that design both algorithms and prove impossibility results, known as lower bounds. So what are these laws? Lower bound is a mathematical statement of the form that no algorithm that has only X amounts of resource can solve some problem P. Now, why are we interested in these kind of mathematical statements? Of course, they show the limits of algorithm design. They tell you what an algorithm can do and cannot do. But at the same time, even failed lower bound proofs often help us discover new algorithmic techniques that help us go beyond what we already do. Now, I have several works building these kind of general techniques to solve problems in modern computational settings. I also have works in algorithmic theory where I build such general frameworks to solve problems together. But for the purpose of this talk, I'll focus on my work in modern computational settings. Okay? So what is a modern computational setting, and why do we need to understand these kinds of settings? Massive data is everywhere. If you look at most applications, it's generating and processing lots of huge amounts of data. However, the memory, the readily accessible memory available in the devices that we use is very limited, like let's say RAM capacity or something. So we want to develop new computational models that take these kind of space constraints into account. Here are some computational models that I have considered in my research. One is a model called streaming algorithms, where a small memory-limited device processes a very large stream using very limited memory. Next, another model is called distributed algorithm, where you have multiple devices. Each device holds some local portion of the input, and then they communicate with each other to sort of figure out something about the global input and compute the algorithm that they have. And finally, the other model is query algorithms, where you now again have a single device, but this device sort of queries random parts of a structured input to gain some information about this input. My research aims to develop canonical solutions to fundamental problems in these different models and identify new connections between them. For the purpose of this talk, I'll focus on my work in streaming algorithms and their connection to these other algorithms in the context of constraint satisfaction problems. What are constraint satisfaction problems? It is a class of combinatorial optimization problem which has wide-ranging applications in computer science. The general structure of a constraint satisfaction problem, also called a CSP, looks like this. In the search version of the problem, at a high level, the question that you're trying to answer is, can you find a configuration that satisfies the maximum number of some constraints? Okay, this sounds very generic. Let's look at a concrete example. Let's say you have a protein folding problem where you have like a string of amino acids. The protein folding problem basically asks you to fold these proteins in such a way so that all these black amino acids you see here, you want those to be as many adjacent pairs as possible. Now, this can be modeled as a constraint satisfaction problem, where the constraint is that you want the black pairs to be adjacent to each other, and you're just trying to maximize this. This indeed leads to low energy protein molecules, and that's what you're interested to compute. Another kind of constraint satisfaction problem is a decision problem, where you want to ask this question: is there a configuration that satisfies all the constraints? Where is such a thing helpful? Imagine an airport which has to schedule flights based on constraints like arrival time, departure time, weather, etc. If suddenly there are some unpredicted changes like sudden bad weather or something, you want to quickly determine if your current schedule is still possible. And if it's not possible, maybe you have to cancel some flights or delay some flights, etc. So these kind of decision problems could be really beneficial in that setting. Now, however, these questions are really hard to solve in general. What I mean by that is you will need a lot of time and space resource to solve them exactly. So we look for approximate solutions, which basically just ask if you can at least solve most of the constraints or something like that. Now, okay, so in addition to the applications of these problems, we also have another reason to study constraint satisfaction problem is that they lead to the development of very general techniques that are broadly applicable. For example, if you consider this technique of semi-definite programming relaxation, which is now sort of used to solve many different problems, it was originally developed to solve a constraint satisfaction problem called max-cut. That was the first approximation algorithm where they used this technique to solve max-cut. Now, indeed, in this case, it turns out that this technique is even optimal, and later it was showed that no polynomial time algorithm can beat the approximation ratio achieved by a semi-definite programming algorithm. And over a decade later, it was shown by Raghavendra that all these techniques can be generalized to solve every CSP optimally in polynomial time. So this is what I'm talking about. You sort of start with one problem, develop some technique, but the CSP structure is so general that it helps you like solve all these other problems simultaneously using the same techniques. Now, my research in CSPs and streaming basically follows this general research thing. So first of all, what is this model, CSPs and streaming? Here you have the constraints which arrive in a stream. You want to use very small space and approximately solve these decision problems. Questions of the form, can you satisfy at least like 50% of the constraint, 80% of the constraint, things like that. Now, okay, so let's say n is the input size. Now, my very first work gave like a small space streaming approximation algorithm for max die cut, which was the first work in this line. And in a later work, we showed that in fact, this algorithm is optimal for any algorithm that uses less than square root of n space. In a later work, we vastly generalized these techniques to show that you can build optimal small space streaming approximation algorithm for every CSP. And finally, in our most recent works, we show how to go beyond these approximations if you use square root of n space and beyond. Now, I have sort of like thrown out multiple terms here, like log and square root of n. What do they even mean in practice? Like, how do I visualize this? So here's how you can visualize these different levels of memory usage. Let's say n is like 1 zettabyte of memory. This is what you want to process. If I have a log space algorithm that's only using like 70 kilobytes, this is something that can fit in an entire cache. And so these are like, you should think of these as like very efficient algorithms because reading and writing into cache is like super efficient. The square root of n algorithms that I mentioned use about like 500 GB of data. And this is like roughly the capacity of modern, RAM capacity of like modern computers. If you go even further, like I can go all the way up to like RAM capacity of like supercomputer using these other more advanced algorithms. And the reason why we would even need such algorithms is because there are critical scientific applications where it is actually worth getting better and better approximations, even if you have to use more space. This is why like all these algorithms are important to study, and sort of based on the application, you can pick the trade-off between whether you need better approximations or you really need to be space efficient. Okay, so this is just to give you an idea of like the different space usages of our algorithms. So here's the talk outline. In the first part of the talk, I'll describe our log space algorithm for this CSP called max die cut, argue why it's optimal, tell you a little bit about how to extend this to like every CSP. And in the second part of the talk, I'll talk about our better approximations that you can achieve using like larger space algorithms. Now, let me begin with some problem definition. I mentioned, the first CSP that I mentioned was this CSP called max cut. Let me start with the definition of that. In the CSP, the input is like an undirected graph, and you want to find a cut. A cut is just like a partition of the vertex set into like two pieces. And cut has a value which is defined to be the fraction of edges that go across. For example, in this example, you have like 4 edges that are across these two sets that I have drawn, and in total you have like 5 edges. So this cut value of this particular cut is 4/5, and max cut is defined to be basically the largest cut value that you can obtain. Max die cut is like a related problem in directed graphs, where the input is a directed graph. Again, you're interested in getting like a bipartition of the vertex set into like two sets. But now these sets are actually ordered. There is a notion of a left set, which is orange in this case, and a right set, yellow, and you measure only the edges that go from left set to the right set. So let's say in this case you have like 3 green edges that go from orange set to yellow set, and you don't count the red edge that goes from like yellow set to orange set. This particular die cut has die cut value 3/5, and the problem of max die cut asks you to just compute the largest die cut value for a given input graph. Now, in a streaming setting, it's that these edges are the ones that arrive in the stream, and at the end of the stream, you want to output whether the max cut or the max die cut, depending on what the problem is. Is the model clear? So, again, as I mentioned before, these CSPs are really hard to solve exactly. In polynomial time setting or streaming setting, you need like full space or like exponential time to solve them. So we look for approximation algorithms. Now, let me formally define what an approximation algorithm is. So every approximation algorithm is characterized by some parameter alpha. And we say some algorithm is alpha approximation if on a given input, you output a value that's at least like alpha fraction of the optimum and at most the optimum itself. Let me give you an example. Let's say I say that I have a 3/4 approximation algorithms for max cut. What does it mean? If let's say my input graph has max cut value 1, then my interval should lie in this, then my output should lie in this interval where it should be at least 3/4 and at most 1. And similarly, if the max cut is 2/3, then the output should be at least half, because half is like 3/4 multiplied by 2/3. That was the definition. You should have at least alpha fraction of the optimum, and it should be at most the optimum itself, which is 2/3 in the case. But if you notice, there's something interesting about these intervals. The top interval is completely disjoint from the bottom interval. What this means is that you can use a 3/4 approximation algorithm to distinguish between these inputs with value like max cut equal to 1 from inputs which have max cut equal to 2/3. These kind of inputs are in general called promise instances, where I promise you it's only going to have one of two values and ask you if you can distinguish these kind of instances. And this gives us sort of a unified way to study algorithms and also lower bounds. Why a lower bound? Let's say I'm actually able to construct an instance of max cut equal to 1 and max cut equal to 2/3 and somehow mathematically prove that no streaming algorithm can distinguish these two instances. What that implies is that you cannot have a 3/4 approximation algorithms for max cut, because I just argued that if you had an approximation algorithm, you can distinguish these instances. And if I prove to you that you cannot actually distinguish these instances, it immediately rules out any kind of 3/4 approximation for max cut. So hopefully I've convinced you that the promise instances are some kind of unified way for us to study both algorithms and lower bounds hand in hand. Now I'll describe some trivial algorithms for these two problems that I defined. Consider some uniform random cut. When I say uniform random cut, just like place every vertex in the left set with probability half and right set with probability half. Now, if you look at this kind of a random cut, every edge is like actually across this cut with probability half. What that means is that the expected cut value is half on every input. Now, if you just output the expected cut value of this algorithm, that immediately gives you a trivial half approximation. So for max cut, the trivial approximation is half. By a very similar logic, using a uniform random die cut, you can show that for max die cut, you can get a trivial 1/4 approximation. It turns out that for max cut though, in the streaming setting, you have no non-trivial approximation. Or in other words, these works of like Kapralok-Kanasudan and Kapralok-Rachan show that in fact, you can construct instances like the maximum gap possible. Like one instance has like max cut value 1 and other almost has max cut value half, such that no streaming algorithm can distinguish between these instances. As I said earlier, like when you show that two instances cannot be distinguished, it already rules out certain kind of approximation. Since here you ruled out 1 versus half, it means since we showed here that 1 versus half cannot be distinguished, it implies that you cannot have a better than half approximation algorithm for max cut. Now I'll give you a little bit intuition about like how these kind of lower bounds work.
Who decides on the order in which the edges appear?
Yes, they should choose a specific order in which the edges appear. I'll soon explain it.
The adversary.
Yes, it is like, yeah. So thanks for the question, yeah. So in fact, like there's a catch here. So you can actually like use a random ordering of the edges. Even then you do have a lower bound, but that only gives you like a square root of n bits lower bound. And if you use like a specific ordering of the edges, that helps you get all the way to n. Very good question. So if you notice that in one case you actually have like a bipartite graph, in another case you have like a sort of a random looking graph. So how is it so that the streaming algorithm is not even able to like distinguish between these two graphs? What actually happens here? So what they do is that they construct the graphs are constructed in such a way that they can be nicely decomposed into these matchings. So it's like, you see, these green edges are a matching because they just like sort of pair vertices, and pink edges and blue edges, they are all a matching. Now, the one property about the matchings on the left side is that they're only matching vertices like between like these different sets. On the other hand, if you look at the right-hand side, it's like a random matching. It could match even vertices within the same set or across the set, anything like that. But locally, when you imagine like just sending the stream, each of these matchings one by one, it cannot really say which is which because it does not have any knowledge of this bipartition. That bipartition is some information hidden from the streaming algorithm. So it does not really know locally which matching is what. And the idea is that unless you store enough sort of information about these matchings, you do not see the global picture. Whether all these matchings are like respecting some bipartition or they are just simply random matchings. So that sort of is the high level idea behind the lower bound. Now, the question is that, okay, but I began this talk by saying that we actually give a non-trivial streaming algorithm for max die cut. So why is it that this whole argument that I just showed you for max cut does not hold anymore for max die cut? Okay, now let's look at some possible graphs you could construct. If you want max die cut equal to 1, what does that mean? All your edges should go from the left set to the right set because that was the definition by which you measured a die cut value. On the other hand, max die cut is 1/4 is again some kind of a random graph where you can only capture like 1/4 of the edges in the bipartition. Now, if you observe, all the edges in the left set, in this first graph, all the edges in the left set have only outgoing edges. And all the vertices in this left set have only outgoing edges. And all the vertices in the right set have only incoming edges. On the other hand, if you look at all these vertices here, they have like roughly half incoming edges and half outgoing edges. So in this particular case, I can even choose to track one single vertex in this tree, look at whether it has all outgoing edges, all incoming edges, or it has like sort of a rough balance of incoming and outgoing edges, and that helps me like distinguish these two distributions. But at a more general level, how do we actually do that? You can define this notion called bias of a vertex, which is basically its difference between the number of out edges and in edges. And bias of a graph to be just this normalized average absolute value of the bias. If you notice that, this left graph has very high bias. The reason is that if you look at the absolute value of this bias, all these vertices are like perfectly biased with only out edges, and all these vertices are also perfectly biased with only in edges. On the other hand, this graph has low bias because, of course, like for whatever edge comes in, you're also losing one edge that goes out. So this graph on average has bias very close to even 0, and that sort of is the idea that we have to use this information to distinguish graphs like this. Okay. Now, how to compute this bias quantity in general? I'll first build intuition for a special class of graphs called bounded degree graphs and show you how to extend this to like general graphs. So let's say we consider a bounded degree graph. A bounded degree graph is a graph where every vertex has maximum degree at most some kind of a constant. Let's say fix a constant 5, and it's like every vertex has degree only at most 5. That's a bounded degree graph. Now, for a bounded degree graph, you can very easily compute this average bias. Just basically sample a few constant vertices and track their biases and compute the average bias. Because it's bounded degree, the variance of this is like bounded, so your average that you compute this way is going to be close to the true global average. And so this is a very simple algorithm to compute bias. But how do we do this for general graphs? For general graphs, if you notice that, you can define this like bias vector for basically a vector of biases for every vertex. And the bias value we want to compute is like the L1 norm. And in streaming, there are standard algorithms that actually help us compute norms of vectors like this. So we use that to estimate bias. Okay. Now that I've given you some idea of like how we compute this bias, what is it actually doing? Why is it that it gives us some? Yeah.
Just to check. Bias of individual vertices, when you're adding them, they're not normalized by degree or anything. You're just literally adding the values.
That's a very good question. So, so we don't normalize it like at each vertex, but like overall or something. You add up all the biases and then normalize by the total number of edges or something. Thanks. So, okay. So I just want to sort of again give you the intuition of like why should we even like care about this bias. So let's say on average, if you have many vertices of high bias, again, as I explained before, what does it mean? You have like, if a vertex has too many out edges and very few in edges, then you naturally want to place it in the left set because then you're going to capture many edges in the die cut and probably lose only a few edges. And similarly, if it has a lot of in edges, you want to place it in the right set so that you capture most of its edges. On the other hand, if a vertex has low bias, then no matter where you place it, let's say I place it on the left set, I'm going to lose all its in edges. And if I place it on the right set, again, I'm going to lose all its out edges. So the idea is that if a vertex has very low bias, no matter where you place it, you're going to lose a large fraction of its edges. And that means that on average, the max die cut value of the graph cannot be too large. Now this is just to build.
So streaming algorithm only keeps track of the L1 norm. So actually, it doesn't know the biases of the individual vertices, right? So can you actually find the cut or just kind of distinguish the two?
Thanks. That's again a great question. We only like find the, okay, so there are two things to it. So yes, what the streaming algorithm outputs is only going to be like the value of the cut itself. It's not going to output, because we are using space even less than the size of the input, we are not going to output the value itself. But you can use this bias information. So let's say like it's like some sort of, once you have bias, you can use it to compute a rounding algorithm that gives you this exact value that you computed. In expectation, this is the value you will have. Does that make sense? Okay. So now this is the exact plot that we do for like the behavior of max cut versus bias. Let me explain it slowly. So this green line here you see is like the upper bound on the max die cut value as a function of the bias, and the bottom blue curve and red curve gives you like the lower bound on the max die cut value as a function of bias. Or in other words, let's say I like measure the bias of a graph to be B, then I know that its max die cut value can only be between this lower bound and this upper bound. That is what this plot shows, and this is the exact plot that we computed in these works. Now, so once we have this kind of a behavior, then the algorithm is quite simple. You compute the bias and just output this lower bound beta of bias. Why lower bound? Because I already said that your approximation algorithm should never exceed the actual optimum. Now, given that the optimum is going to be in the range beta of B to gamma of B, the only thing you can do is like output beta of B. And so the approximation ratio itself, in the worst case, your actual graph could have max die cut value gamma of B, but what you output is only the lower bound, which is beta of B. So the approximation ratio is like measured by the ratio of these two curves. And in the worst case, what is the worst case approximation of this algorithm? That's given by the largest gap between the upper and the lower bound, and which happens somewhere here, and the ratio we get is 4.9. It's the algorithm. Okay. Now, it also turns out that this algorithm is actually optimal. That is what I'm going to show in the next slide. What do I mean by the algorithm is optimal? Again, to explain this, we study this through these promise instances. The question is like, now let's say I give you two values, gamma, beta. I want to understand, when can I distinguish graphs with max die cut value gamma from graphs with max die cut value beta? Okay, so let's plot this here. So let's say I look at graphs with max die cut value gamma. Now in this plot, I gamma is the interval of possible biases for any graph with value gamma. If you look at beta, again, I beta is the interval of possible biases for any graph with max Likert value beta. Now here is our dichotomy theorem. If these intervals actually do not intersect, then you can use bias to compute them. If these intervals are disjoint intervals, then you know that just by looking at the bias, you know whether the instance has value gamma or the instance has value beta. But interestingly, the lower bound is that if the intervals actually intersect, you know that you cannot use bias to distinguish them. But we show that there is no streaming algorithm that uses less than square root of n space and can distinguish them. It's not just that bias cannot distinguish these kind of instances. In fact, no streaming algorithm cannot. So sort of the high-level takeaway here is that in log space, either you can use just this bias quantity to optimally distinguish instances, or whenever you cannot distinguish them with bias, no algorithm can do that. Okay? And very interestingly, this also extends to every max CSP. So if you look at any constraint satisfaction problem, these plots are going to be different, but still, there is, like, we should give a framework on how to compute them. And we have this general dichotomy theorem, which shows that there is a general notion of bias, which shows that if you have these kind of intersecting intervals, your bias can, if non-intersecting intervals, your bias can distinguish them. On the other hand, if you have like intersecting intervals, in fact, no algorithm can distinguish these kinds of instances. That's like our general framework for all CSPs.
So it's more or less clear from the contents, but still, all your algorithms, you don't care about internal complexity of these algorithms, right?
Sorry, the space complexity is what
space complexity is okay, but the algorithm need not necessarily run in polynomial time or whatever.
Yes, they do run in polynomial time, but it's not something we like measure or something. So
the lower bounds don't care about the
yeah, the lower bounds don't care.
Sorry,
lower bounds, Thanks, So the lower bounds don't care. The lower bounds have only like space restrictions.
But still, or concrete it's very simple. Concrete algorithm is very simple.
The concrete algorithm, exactly. The concrete algorithm we do is like very simple. It is a polynomial time algorithm, but the lower bound is against even exponential time algorithms. The lower bound only cares about space.
Don't care about algebra space.
Thank you. Okay, so now I'll give you some sort of like high-level idea about how we even prove this lower bound. So, we want to prove lower bounds when instances have these intersecting bias intervals. So first, let's begin with this max cut graph that we saw earlier, where we showed that we cannot distinguish a value 1 from value half. Now, you can convert this into a directed graph by just like take every edge and add to sort of like directed edges. In place of every single undirected edge, you add 2 directed edges going in 2 directions. Now this is like an unbiased graph. Now we add some edges to make the whole of bias B to make both these graphs have resultant bias B. And this new graph, the left graph has like max Likert value at least gamma, and this other graph has max Likert value at most beta. So while originally the lower bound show that you cannot distinguish like those unbiased graphs in like less than n space, these biased graphs, we can only show that you cannot distinguish them in less than square root of n space. The question is like, why is it like square root of n? Is it just that is there some kind of a fundamental limit? Why is it only square root of n? I'll give some intuition for at least this particular graphs, what happens. Now, my claim is that the limit is square root of n because if you look at this previous diagram, while individually these graphs are indistinguishable in n space, and what we added was exactly the same portion, like the same edges are added to both the left and the right instances. Once you sort of combine these 2 graphs, there is some information that you're able to gain from these new biased edges that only gives us like a square root of n lower bound. And I'll soon explain why that's the case. Now, in all our constructions, graphs have only boundary degree. So you have only like order n edges. Now, if you notice that all these orange vertices have positive bias because originally you started with 0 bias vertices. Now you added like bias edges between these partitions. So all these orange vertices have positive bias. Yellow vertices have negative bias. The one thing to notice about these two graphs is that you don't have any edge here within the same set of like positive bias vertices and no edge between negative bias vertices. On the other hand, in this graph, you do have edges within positive bias vertices or you have edges within negative bias vertices. My claim is that this is something you can detect in square root of n space. How do we do that? Just sample some square root of n random vertices, track the biases in the stream, store the induced subgraph, just look for an edge. See if you have an edge in this like left set or in the right set. And if you do find an edge, then you know that you're from the second instance, else first instance. But why is this square root of n here? Reason is because you need to sample at least that many vertices to even see one edge or constant number of edges. Because when you sample square root of n random vertices, it means that every vertex is sampled with probability 1 over square root of n. And as I said here, you have like n edges in the graph. So each edge is going to be sampled with probability 1 over n. So you can, to even see some constant number of, this is also called like birthday paradox in CS, but anyhow, so this is the reason why you need to sample at least square root of n random vertices to see some edges. And that's why we have this limit of square root of n in the lower bound. Okay, all right. So I have showed like the log space algorithm for max die cut, why it's optimal, and then also showed that in general, the same intuition can be extended to all CSPs. Now I'll tell you a little bit about how to achieve even better approximations when you use square root of n space and beyond. Before I delve into the actual details of our algorithm, let me give you a very high-level picture of how our algorithms work. For that, let's first look at classical algorithms. What do? They take as input the whole graph, and they actually output a die-cut partition. And how do you measure the approximation ratio of these algorithms? It's like these algorithms could potentially use random coin tosses. So their approximation ratio is measured as the expected die-cut value they produce to the ratio of the true max die-cut. This is how a classical algorithm works. Local algorithms are again like algorithms which like produce like outputs of which produce an entire die-cut partition, and their approximation ratio is measured the same way. But one difference is that for a local algorithm, if you're trying to decide where to place, let's say, this vertex B, it only has information about the local radius neighborhood. So let's say like a radius k neighborhood of this vertex, that's all it can see to decide whether or not to place vertex B in the left set or the right set. This is sort of a rough definition of a local algorithm. Is it clear? Okay. Now, our idea is that you can compute some kind of average neighborhood statistics in streaming. Once you compute these kind of statistics, you can use it to compute expected die-cut value of local algorithms. So if you recall, like local algorithms themselves have to actually compute the die-cut partition. In streaming, we are only interested to compute the max die-cut value. So all we show is that in order to just get to the die-cut value of the local algorithm, you only need some kind of statistics about the average neighborhood of vertices in the graph. And we show how to compute these kind of statistics. Okay, now first let's see what kind of statistics can we compute in square root of n space. I'll again start with some assumption that graphs have bounded degree to build some intuition, and then show how to extend this to like arbitrary graphs. So let's say you have bounded degree graph. We already showed that it is possible to detect edges, to see if you have edges within, let's say, biases of like between positive bias vertices or within like negative bias vertices. This is something you can actually generalize. You can sort of partition this entire vertices into some constant number of bias classes and ask for this question, like how many edges go from like one bias class to the other. You can imagine this as some kind of edge statistics of this graph where you're coalescing vertices based on their bias into just like a few bias classes. In the previous algorithm, you could have even computed questions you could have answered questions like how many fraction of edges are within positive bias vertices, or how many fraction of edges go from positive bias to negative bias vertices. This is basically like a generalization of that concept. We call this kind of a condensed graph a snapshot of the graph, a snapshot of the original graph. Clear? So now, the same algorithm is not going to work for general graphs. Why is that the case? So let's say that I actually take this kind of a star graph where you have one central vertex and n outer vertices. if I sample square root of n random vertices, with high probability all the vertices you sample are going to be the outer vertices. And the induced subgraph is just like the empty set with no edges, so you gain no information about the max die cut. So in this case, for general graphs, you really need to sample vertices with probability proportional to their degrees. But what is the issue? Recall that in the streaming setting, you get the edges in a stream, so you do not really know what the degrees of the vertices are in advance because you only see one edge at a time. There is no information you have about the degrees of the vertices. So one way to mitigate this is you can now actually sample random edges because that's what comes in the stream and look at their endpoints. Why does this help? So let's look at a vertex which has like degree 4 versus a vertex which has degree 2. This vertex has more edges incident to it. So if you pick a random edge, U is twice as likely to be sampled as V. So in that sense, if you look at random edges and take their endpoints, those are going to be very proportional to the degrees of the vertices. What's the issue with that? This particular thing, you need to track their biases. The moment you sample a random edge and look at its endpoints, before that, let's say U is sampled at some time t, in the previous t-1 time steps, any of the other edges could have arrived. So you did not track the bias information till that point. So if you track it after this point, you would not be able to compute it correctly. So what we do in our paper is like some kind of like clever interleaving between both vertex sampling and edge sampling to achieve both these things that we want. We want to sample vertices proportional to the degrees. At the same time, we want to keep track of their biases. So we sort of interleave these two algorithms to achieve both of this for general graphs in square root of n space. So this is a high level idea. After all this, what I've showed is that in square root of n space, you can compute these kind of snapshots. How do we actually use it? We use it to simulate a kind of local algorithm called oblivious algorithm. Now, using the snapshot, we can compute the expected die-cut value of any oblivious algorithm. And these kind of algorithms were studied by Feige and Joseph for max die-cut, where they showed that it is possible to achieve like 0.483 approximation for it. And this is some value strictly bigger than 4.9, so that's why immediately we get some new algorithm that beats our best log space approximation algorithm that we had using bias. And we also, like in a very recent work with students, I improved this algorithm slightly. Now the question is like, can we get all the way to half approximation this way? Just wanted to quickly recall why this factor half is like important. So recall that we had this reduction where we started with graphs showing that max cut you cannot do better than half approximation. And, we started with graphs showing that for max cut you cannot do half approximation. And by adding these directed edges, you can also show that for max die cut, you cannot get better than half approximation in n space. The question is that can we get all the way to half approximation for oblivious algorithms? And the answer is no, because there are limits to the approximation that can be achieved by an oblivious algorithm. So the question is like, okay, now can we get all the way to half approximation? Are there other local algorithms that help us get there? Yes, indeed. There are these algorithms called distributed algorithms, which achieve half approximation for max die cut, and we are able to simulate these algorithms in streaming. So let me quickly go over this model. In distributed algorithm, you have like an underlying technique and a bunch of computers that underlying network and a bunch of computers that are connected on this network. Each computer sort of looks at some local portion of the input, and they're allowed to communicate with each other. You're only allowed to communicate with your neighbors, and yeah. So for distributed algorithms on graph, we have a graph, and the model is that each vertex in the graph is itself a computer, and a vertex can communicate with all its neighbors. Now the communication happens in rounds, and let's say in first round, you got this red message from all your distance 1 neighbors. In the second round, you can get messages from your distance 2 neighbors, and in third round, in this example, you can get message from your distance 3 neighbor. Or in other words, if you want to get some message from your distance k neighbor, it takes roughly k rounds to get that message to you. Now, for distributed algorithm, there's this work of Santhoshini, Levy, and Shachnai who show that if you just use like 1 over epsilon rounds, you can get half minus epsilon approximation in this setting. So now what we show is that you can actually compute like radius k neighborhood statistics, which is a generalization of the edge statistics we saw before, and using only like little of n space for bounded degree graphs. Now, using this radius statistics, you can actually compute the expected die cut value. So why k+1 statistics for k round? Because in the beginning itself, you have information about your neighbors. And in the first round, you'll get information about your radius 2 neighbors. And in k rounds, you can get all the information you need about your k+1, at most k+1 distance neighbors. So at a high level, if you know everything about your distance k+1 neighbors, that is enough to compute what the particular assignment for each vertex, and that overall helps you compute the die cut value. And the exciting thing about our result is that this kind of a reduction also gives a new lower bound for distributed algorithms. Until our work, it was not known that half is the best possible approximation for distributed algorithm in constant rounds. Now, because of this reduction, what we have showed that in distributed setting, you cannot have better than half approximation in constant round. So this kind of a new connection also proves like new limits for distributed algorithms. Okay, so for coming to future directions, one concrete future direction I have is to actually study distributed algorithms for CSP. Well, these are well studied in the AI literature with multiple different methods. These methods do not have theoretical guarantees. And in theory, except for like specific problems like max cut and max die cut, there are no distributed algorithms for general CSPs. So my aim is to build a general framework again for like in streaming to develop new distributed algorithms for all CSPs. And also answer this like question of whether distributed algorithms yield the optimal little open space streaming approximation algorithm for every CSP, thereby sort of connecting these two different models. And also hope to apply these insights more broadly to other problems. In addition to my research and theory, I'm also interested to sort of develop more efficient solutions in practice. For example, in theory, often we assume the inputs are the worst case inputs. But in practice, you could use some additional structures of the inputs and solve them more efficiently. For example, in all my algorithms and lower bound we saw so far, we assume that the adversary chooses the orders of the string. But in fact, if you consider random order string, you can do many of the algorithms I mentioned more efficiently. In particular, all these neighborhood statistics can be like exponentially more efficient. Instead of like square root of n space or even n to the order 1 space, you can compute everything in just logarithmic space. And in another problem in streaming, a famous problem called heavy hitters, where you're trying to detect like elements that occur most frequently in the stream. In a recent work with Hua Cheng Yu, we show that in fact even this problem can be solved more efficiently if you consider like random order streams. Now another direction that I'm interested in is to like study more realistic computational models. For example, if you look at a vanilla streaming algorithm, the assumption is that it absolutely has no knowledge of the future input. But if you think about it, why should we just allow one pass through this input? Maybe you can allow like one additional pass if it really helps you get even more efficient algorithms. The question is, can you actually improve an algorithm's efficiency by allowing more passes? Even for this question, we answer in the positive. In fact, you can get exponentially more space efficiency. For example, the snapshot algorithm that I just mentioned, if you allow one more additional pass, even through an adversarial stream, you can now compute snapshot using just logarithmic space. And the general radius key statistics, we again give a k-pass algorithm for computing those statistics using just logarithmic space. What about other methods? So this is not the, allowing more passes is not the only way to get some idea of the future. There are also some ML models that can sort of predict to what the future input can be. Can we use these kind of like models to get better algorithms? This area of algorithms is called learning augmented algorithms, and it's something I hope to also explore in the future to see if we can design more efficient algorithms. Finally, as a summary, my broad goal is to like devise canonical solutions to fundamental problems that are broadly applicable, develop unified techniques to do both algorithms and solve prove impossibility results, discover new reductions that can connect different models of computation, and finally to design more efficient algorithms in practice. While most of my works fall under the setting of like modern computational setting, I also have works in algorithmic game theory, and all these fit under this broad umbrella of like optimization under incomplete information. In this setting, you have incomplete information because you basically don't have enough memory to store all of it. And in algorithmic game settings, typically you have strategic agents sort of manipulating the input. So even though you see some parts of the input, that only helps you like infer something about the true input, but you don't actually know what it is. And I like to think about these problems more broadly. Thank you.
A bit of time for questions. I have one. You mentioned beyond word scale. Is there also a notion of like semi-random models for streaming?
Sorry, semi-streaming or semi-random?
Semi-random.
Yeah, semi-random models. So maybe
Oh,
some
so
part
like
is
not
adversarial,
random.
some part is random. But yeah.
That's a good question. So yes, I think there are some models like that, but actually, yeah, I have to check back on that. So I'm only aware of works where they consider that the input is from some kind of distributions and then have algorithms for those, but I'm not sure if there are anything where a part of the stream is random, but part of the stream is adversarial. At least I am not aware of it.
I mean, I'm speaking for Yuri. I mean, like he can do really amazing things with like just a little bit of randomness in
Fair
there,
enough.
right? So just trying to.
Yeah, interesting question. Yeah, though I don't know the answer.
Other questions?
Yeah, I was wondering for dense CSP, is it fully understood what you can do in streaming?
Okay, that's a very good question. So in streaming, actually, there's no difference between like dense CSPs and sparse CSPs. The reason is because like you can actually like sparsify every CSP to get like just whatever the resulting instance is like 1 minus epsilon approximation to it. So what I mean by that is like, let's say you actually take a max cut instance. Now you can like just sample like n over epsilon square edges such that the resulting CSP instance has 1 minus epsilon approximation to it. So you just sort of sample on the fly, look at the sparse instance and do whatever computations on the sparse instance. That's not going to lose you much approximation.
So I guess I don't, like, shouldn't dense be easier? Maybe I'm too slow.
Yeah, it's like, shouldn't you want to densify things?
Oh, so like easier in what sense? You still have like sort of limited space. So I'm not sure.
Like for dense max cut, it's like easier than sparse max cut.
I don't think it's easier. Yeah.
Like in classical algorithms.
Yeah, sorry, I meant in streaming. Yeah. Again, very good question. Thanks. Yeah.
Questions?
I guess randomization was crucial, right?
Yes.
With randomization, you guess a few random vertices, and use them as an estimate. But I guess if you're deterministic, probably you can't do anything. Is that true?
That's a very good question. So we don't have any formal proofs right now, saying that deterministic algorithms can't do anything. But at least it's my belief that you won't be able to do anything. But yeah, no, there is no formal any study on deterministic algorithms for CSPs.